shades, man, looking like pennies with it.
He's the preacher?
Yeah.
Wow.
And he's fantastic. He's just as good of a preacher as he is a teacher.
Cool.
If not better. He ruined it for every other church I've ever been to.
That was definitely an experience.
It was awesome.
Is it going to like 1:30?
Yeah.
That's the way.
Well, getting out of there was also the hard part because everybody wants to stop and talk to you.
Yeah. It's easy to find visitors when the only communication in the church are the visitors.
Well, it was the funny part because at the start of the sermon, they wanted to introduce all the guests. And
Yeah, I
stuff.
know. And I didn't want to say that, but we had to.
It was totally obvious.
Introduce yourself?
Yeah.
You have to say what you're about or anything?
No, we just said our name.
What church we were from.
Yeah.
And then I also told the congregation we were students of Mr. Williams.
Okay. What is the you said denomination? Baptist? I think I would like to get that, except for the introducing part.
Most fun I've ever been to church.
Well. How's life? Good? Enjoying your summer?
Oh, yeah.
Except for the physics? Or
No,
including
that's my
the
favorite class, actually.
really? Cool.
I can't do literature.
I hate history. I failed history. Physics makes sense.
I feel for you. I can identify with that. You're taking EMAG right now, right?
Unfortunately, yes.
Yeah. Just talked to a gentleman here, and he's dreading taking EMAG. I think he's going to take it next.
Luckily, we have like a good teacher that only teaches it like once every 2 years.
Oh, okay. All right.
He's an actual engineer. So.
He's actually taught before.
Yes.
That's good. Well, we've got a test coming up on Monday. Yes? Yeah, just to kind of just solidify everything, finish a section, and then go on. Right?
Did you say we could work in groups on that?
It's a take-home test.
You don't want to take home tests.
No, I do not want to take home tests.
Not especially for this kind of stuff. So, I mean, you can work in groups. I've told you that I'm just taking the problems straight from the problem sets, and there are some hard ones in there. So, you just have to just make sure you do them all. Yes. Yeah. But if you do them all, then you're in good stead, right? So,
The problem is once you're done with all of them, you like forgot how to do the first one.
Yeah.
So I thought the first thing we could do today, before we finish up chapter 22, is go over a few of these problems, a few extra problems. All right? And so let's start with chapter 20. And take a look at, for starters, number 25, chapter 20. So dark up here. Is it better if that light's on? Chapter 20, number 25. 2 kilograms of water at 100 degrees Celsius are converted to steam at 1 atmosphere. Find the work done in joules. Density of steam at 100 degrees Celsius is 0.598 kilograms per cubic meter. All right, so we're making a phase change, phase conversion. But in doing this, we're not necessarily asking for the heat added when this phase changed. pressure times the change in volume by the gas. And the final volume is going to be greater than the initial volume. So we need to find, well, the pressure is 1 atmosphere. That's going to be 1.013 times 10 to the 5 newtons per square meter. We need to find the initial and the final volume in order to do this. So what is our initial volume?
Would be mass divided by.
Yes, the mass divided by rho. Mass divided by the density of water.
Let's see.
Well, initially we're starting at with water. Liquid water.
Okay.
We got 2 kilograms, and the density of water is 1,000. Put units in here. 1,000 kilograms per cubic meter. So our initial volume is 0.002 cubic meters. Then we're going to convert that to steam. And so our final volume will be the mass of the steam divided by the density of steam. And so again, that will be 2 kilograms. But we're told that the density of steam is 0.598 kilograms per cubic meter. So if we calculate this out, I didn't bring my calculator today. 3.34. There's our initial and final volume. So the work done is the pressure times the change in volume, which would be 1.013 times 10 to the 5, times the final volume minus the initial volume, which would be 3.34 minus 0.002. So, what is that?
3.37 times 10 to the 5th.
3.37 times 10 to the 5th joules to the work done.
Got a question.
Yes.
When you convert a mass of water to steam, will the volume always be proportional to your mass? Is there a constant relationship?
Not necessarily.
Could sum on pressure.
Yeah. I guess we're given this steam. It depends on the temperature and pressure of the steam.
Okay.
So in this particular problem, we were given that density, but that can be different.
Okay.
Yeah. Good point. Look at 26, which is kind of related. 2 kilograms of water at 100 degrees Celsius is converted to steam at 1 atmosphere. Same premise. Find the change in internal energy. Well, we're doing the phase change, so the heat added would be the heat associated with the vaporization. That would be the mass times the latent heat of vaporization at 100 degrees. And we have 2 kilograms, so that's going to be, I was thinking this latent heat of vaporization in terms of calories. Given in the problem, 2.26 times 10 to the 6 joules per kilogram. So this will give you 4.52 times 10 to the 6 joules. So the change in internal energy is the heat added to the system plus the work done on the system. That's going to be 4.52 times 10 to the 6 joules. Plus or minus 3.37 times 10 to the 5.
You should be fine.
It'd have to be minus.
Steam's doing
We want the work done on the system, not the work done by the system. So we'll have to use the negative of this. And see, one's 10 to the 6, one's 10 to the 5. So the 4.52 minus 0.337 gives us what?
440.
10 to the 6. So that'll be the change in internal energy. Take a look at number 30 in chapter 20. It says the Earth intercepts 1.27 times 10 to the 17 watts of radiant energy from the sun. Suppose the Earth, a volume 1.08 times 10 to the 21 cubic meter, was composed of water. How long would it take for the Earth at 0 degrees centigrade to reach 100 degrees centigrade if none of the energy was radiated or reflected back out into space? All the energy that's coming in is going into the process of heating up the water. So we got the Earth, and it's comprised, I don't know how to symbolically do that, comprised entirely of water. The volume of the Earth is given as 1.08 times 10 to the 21 cubic meters. And incident on this is some radiation from the sun. My Earth kind of looks like the sun, doesn't it? There's the sun.
That's what we make.
From the sun? Yeah, but that's the solar corona.
I think it looks nice.
And the sun's kind of small right there.
I think it looks like, well, because it's far away, I'm drawing with perspective. Right? See, that's an advanced drawing technique.
It's got a little squiggly line in between.
Are the little lines,
Mine's third grade, sorry.
are the little lines on the top of the Earth, is that like the Aurora Borealis? Is that right?
Exactly. It's actually, no, it's the corona. It's the
Okay.
solar corona. Yeah, the Aurora Borealis is over here.
No.
Looks like an amoeba and another cell-like organism. Or was that?
The sun radiates.
The power coming in to the Earth is 1.27 times 10 to the 17 watts. So that's a joule per second. We're going to figure out how long it would take for the Earth to go from 0 degrees centigrade Celsius to 100 degrees Celsius. So we need an amount of heat equal to the mass of the Earth times the specific heat of the Earth times the change in temperature of the Earth. And so for the mass of the Earth, comprised of water, this would be the density of water times the volume of the water times the specific heat of water, which times the change in temperature. Final temperature will be what?
100 degrees. Wait. 370.
We,
But it's the change, so you don't really get it.
exactly.
Change.
It's a change in temperature, so we can actually,
It's nice little habit.
it's good to have to just go to Kelvin. I'll agree with that. Let's do that. Just so you don't make mistakes on other problems. 373 minus 273, which will still give us a change in temperature of 100. So it's just a good practice to do that, just so you don't make, it'd be so easy
Yeah.
to not make that conversion on another problem. Density of water, 1,000 kilograms per cubic meter. Volume of the water is the volume of the earth in this case. Specific heat of water, 4,186 joules per kilogram. And 100 degrees change. I put all that in. What do I get? 4.52 times 10 to the 29. Joules. That's great. I kind of like this having help.
So take that number and divide it by P.
Right, because power is energy per time. In this case, the energy we're talking about is the heat energy. So in this case, it'd be equal to heat energy per time. So the time is going to equal the heat energy per power. And so that's going to be 4.52 times 10 to the 29 joules divided by 1.27 times 10 to the 17 joules per second. What does that give?
3.56 times 10 to the 12.
3.56 times 10 to the 12 seconds. Let's convert this to years, knowing the rule of thumb that I gave you on the first day of Physics 1, which was how many seconds there are in a year, roughly.
Pi times 10 to the 7.
Pi times 10 to the 7, very good.
Wow.
I watched the video.
Oh,
2
okay.
days ago.
I was gonna say, good job.
Oh, you should have told me that. That was pretty impressive. If we say that 3.56 divided by pi is roughly 1, then 10 to the 12 divided by 10 to the 7 will give us 10 to the 5 years. 100,000 years. I guess more accurately it would be 1.13 at 10 to the 5 years.
10,000 years, wouldn't it?
100,000 years.
100? Since the pi? Okay, yeah.
Which actually, in terms of the life of the Earth, is actually a very short time. So we'd be blown after a while. If the Earth's been around 4.5 million years,
Good.
billion years. We've been around 4.5 million years. Earth's been around 4.5 billion years.
There are those people who would argue with you over that.
I know. I hope that none of those people are ready to do that right now. I'll go to church on Sunday. They'll help me. Okay, anything else in chapter 20? We're ready to go on to 21?
Ready for 32?
Yeah, let's take a look at 32. That's an interesting problem. On to 32 in chapter 20. a 100-kilogram marble slab falls off a skyscraper and falls 200 meters to the ground without hitting anyone, which is a good thing. Its fall stops within milliseconds so that there is no loss of thermal energy to the surroundings if its temperature is measured immediately after it stops. By how much has its temperature changed as a result of the fall if we ignore energy gained or lost as a result of its interaction with the atmosphere? Here's the building. I'm putting a little perspective in there. There's the street coming in like that, so it kind of gives you that feeling that so I've been taking drawing lessons. Little tree there.
Little happy bird.
What is that down glass?
Yes.
Drawing lessons from the school of Picasso.
It reminds me of the glass bags or whatever, the commercial falls off the building, holding out. And then it just falls like right next to him, so you pick up all the pieces, put it in that trash bag, take it upstairs.
Oh, really? All right, we have a marble slab, 100 kilograms. It's going to fall 200 meters. That's H. And we want to find how much the marble slab is increased in temperature. We're given the specific heat of marble. All right. So, what should I do?
Well, I'm thinking that take the potential energy that you have. This not even worry about, because we know the potential energy of top is kinetic energy.
Correct.
Right. So we just do MGH, and that energy that it has would we would say that's equal to
Yeah, we're going to go straight because we were given the rules to violate the laws of thermodynamics and just say that all the energy we start with went into heat. All right, so I think that's a good thing to do. So we're just going to say heat is equal to MGH, potential energy we start with. So that's going to be 100 kilograms times 9.8 times 200 meters gives me what?
1.96 times 10 to the 5.
1.96 times 10 to the 5 joules. And we want to have all this energy go into heating up the marble. So the heat would equal the mass of the marble times the specific heat of marble times delta T. We'll solve for delta T. So that's going to equal the heat divided by the mass divided by the specific heat of marble. 1.96 times 10 to the 5 divided by 100 kilograms and divided by 860. Based on all the units, this should give us the answer in degrees Celsius. What is that?
2.28.
2.28. And since a degree Celsius is 9/5 of a degree Fahrenheit, I would say approximately almost 2, so this would be about 4.5 degrees Fahrenheit.
No. That would have to be, that number would have to be greater than 32 degrees.
There's just a change in temperature.
Oh, okay,
chapter 20. So good? Is that the hardest chapter? The longest. What about 21? Got a request for 11 and 13. This is like the shorter chapter. Take a look at problem number 11 from chapter 21. It says, during the volcanic eruption of Mount Pelee in 1902, an incredibly hot, burning cloud rolled down the mountain and incinerated the town of St. Pierre. Why is it all the physics problems are all dramatically catastrophic?
I guess thought we're doing something.
Less percent.
Josh?
All physicists and engineers are somehow equally just mentally twisted.
I'm not sure about that. I do think the problem would be better if there were, a bunch of burning lemmings, No, I'm just saying. From the damage done, the temperature in the cloud was estimated to be 700 degrees Celsius. If the air temperature was 20 degrees Celsius, and the molecular weight of air is 29 grams per mole, I guess, estimate the molecular weight of the gas in the burning cloud that made it heavier than the surrounding air. As a follow-on, estimate the most probable composition of the cloud. Some typical volcanic gases are hydrogen sulfide, sulfur dioxide, sulfuric acid, carbon dioxide, and nitrous oxide. Okay. I think what we have to assume is that the velocity, the RMS velocity of air is equal to the RMS velocity of the gas. The RMS velocity of the air is 3R temperature of the air to the molecular weight of the air. That's equal to 3R temperature of the gas to the molecular weight of the gas. Square root. If I square both sides, I'll get this. Get rid of the 3 R's. Solve this for the molecular weight of the gas. Right, the molecular weight of the gas is going to equal the temperature of the gas over the temperature of the air times the molecular weight of the air. What was the temperature of the gas? 973 K. Thank you for making that conversion automatically for me. Yep. And the temperature of the air? 293 K times 29 grams per mole. If we were to make that calculation, 973 over 293 times 29, what did you get? Grams per mole. That's the molecular weight of this gas. some possibilities for the gas that are given. It's typical volcanic gases. Oh,
H2,
H2S, not water.
H2SO4.
H2S, SO2, H2SO4, carbon dioxide, nitrous oxide.
The only one is H2SO4.
Yeah, the only one that, sulfur is molecular weight 32, oxygen is 16, hydrogen is 2, so this one would be 34. This would be 32 plus 32, 64. This would be 2 plus 32 plus 64, gives us 98. And this would be, 14 plus 32, 46. 12.
So,
14 is nitrogen.
I knew I was wrong when I got to the nitrogen there. All right, so there's our candidate. Boy, that would have been fun. A hot gas at 973 Kelvin, and it's comprised of sulfuric acid.
Well, if you gotta go, I would prefer the nitrous oxide.
Yeah, you'd be laughing, right? We should joke about that, I guess. That was in 1902. That was more than 100 years ago, I guess. That the statute of limitations is exceeded. Just kind of reminds me of Venus, right? Sounds like what it'd be like on Venus. Problem number 13. Air expands adiabatically, no heat in, no heat out, from a temperature of 300 K and a pressure of 100 atmospheres to a final pressure of 1 atmosphere. Treat the gas as ideal with a gamma of 1.4 and determine the final temperature. Compare your results to the boiling points of nitrogen and oxygen. Could this method result in the liquefaction of air? Start over here. Well, I actually derived a formula for you we have several formulas for adiabatic change in volume. And the first one was P, V to the gamma, initial equals P, V to the gamma, final. And T initial, velocity initial, the gamma minus 1 was T final. Did I say velocity? Volume final, or gamma minus 1. And there was one I derived just in case you would have a problem like this. And I think it went something like this. Let's see. It takes a little bit of algebra to do that. Is that what it looked like?
They switched.
Switch?
The fractions are switched.
Gamma minus 1 over gamma?
It's plus 1 minus gamma instead of gamma minus 1.
Like this, or? Okay. Now this is the one we want to use on this problem. So we want to solve this. It said we know that the T initial is 300K. And P initial is 100 atmospheres. So we're going to keep it like that because we're going to be interested in a ratio. Gamma is 1.4. And P final is 1 atmosphere. Right? So what's T final? T final is going to equal T initial times P initial divided by P final to the 1 minus gamma over gamma power. Just taking this and dividing it over here. So that'd be 300. P initial was 100. P final is 1, so the ratio will eliminate the units. So it's just a number. So 1 minus 1.4 over 1.4 is 300 times 100. So the negative 0.4 over 1.4. Or I guess you could reverse that, right? And say that it's 300 times 100 to the, right, 1.4 over 0.4. No, I'm going to do it. Let's just do it that way so I don't get in trouble. So what is that?
80.5.
80.5? Cal? By reducing the pressure in this adiabatic process, we can cool it pretty well. And it says compare your results with boiling points of nitrogen, nitrogen being 77.4, not quite enough to liquefy nitrogen, but oxygen has a boiling point of 90.2, so it would be good enough, this process, particular process, would be good enough to liquefy oxygen over gas.
So could you actually separate nitrogen and air by having nitrogen and oxygen?
That'd be one way to do it.
Cool. Would that be more expensive than doing it electrolytically? Is there-
I don't know. I don't know what the cost is. It just seems more logical to do it that way. Liquid, yeah, you get liquid oxygen.
Separate nitrogen and oxygen.
You get gas.
Gas.
Yeah. So I don't.
It seemed like it's more efficient.
Yeah. Yeah. Seems you get the liquid out of the combination of gas. It seems like a good idea. Anything else in chapter 21? Let's take a look at the last part of chapter 22. time we introduced the second law of thermodynamics, and in the process of that, we introduced a concept called entropy, and today we want to expand on that a little bit. Think of entropy as a state variable. A state variable is something that relies on the present condition of the substance, the gas at that moment. So a state is an absolute condition. And so as a state variable, it's something that is, if you have that situation, it's not going to change due to the way that you achieve that situation. It's just an absolute condition of that gas. Here's a state review of thermodynamics so far. We had the zeroth law, which basically had the purpose of defining what temperature was. We had the first law, which is basically the conservation of energy. The second law introduced this concept of disorder, which we call entropy. And we never really will talk about the third law, but the third law has a concept where if you take the state variables, or as temperature approaches zero, your energy will approach zero, and the entropy will approach zero as well. So it's not anything that we're going to expand upon beyond this statement here. State variable, these variables depend on the present thermodynamic state of the system, not necessarily on the path that brought it to that state. So not as opposed to transfer variables like heat and work. To try and understand entropy a little bit better, let's define what we might call microstates and macrostates. In statistical mechanics, the conclusion is that isolated systems will tend toward more disorder, hence more entropy, which we designate by S. And we say that S is a natural measure of the disorder at that moment as a state variable. So entropy itself, S, measures the state of disorder at that moment. What would this really mean in terms of a system? Well, if we think of a system macroscopically and microscopically, in a macrostate, we have a description using macroscopic variables such as pressure, density, and temperature to describe that state. So it's more of a general accumulation of everything summed into these concepts of pressure, density, and temperature. A microstate, on the other hand, would be a particular configuration of the very individual components of that system. So if you had a system, say a gas, it's under a certain pressure, density, and temperature, if we were to freeze that gas at a moment and look at what everything was doing at that moment and what everything was at that moment, that in particular would be the microstate. For a given macrostate, a number of microstates are possible. And it's assumed that all microstates are equally probable. So any kind of particular configuration of a macrostate at any moment would be a microstate, and we can think of all those possibilities for that macrostate as being equally probable. For instance, it's all a matter of probability. If you look at all the possible macrostates, all the microstates associated with macrostates, you find that a macrostate that has more microstates has more disorder. In other words, has more, far more microstates associated with disorder than you do with order. All right? And that just means that if every microstate is equally probable, then it's less probable to have a macrostate that has more order because you have less microstates associated with that macrostate. Make sense?
Not really.
That'll make more sense when I show an example. I think. The probability of a system moving in time from an ordered macrostate to a disordered macrostate is far greater than the probability of the reverse. The probability of going from a macrostate that has a certain number of microstates to a macrostate that has more microstates is more likely than the reverse. Because simply each microstate has equal probability, and it's just more possible to have these more microstates from a given situation to start with. If we consider such a system and its surroundings to be the universe, then the universe is always moving towards a macrostate corresponding to greater disorder. Let's give an example. Here's two card hands. On the left is the usual hand that I might get. I was playing cards. On the right is a royal flush. You got a royal flush and a crummy hand. Now, if you were dealt 5 cards, just out of the deck, then the probability of getting this particular hand with 2 of spades, 3 of diamonds, 7 hearts, 3 of clubs, queen of diamonds, the probability of getting this particular hand and the probability of getting a royal flush with spades is equally the same. And you've just been dealt 5 cards, and this particular hand, crummy hand, and this particular royal flush have equal probability of being dealt with 5 cards. However, if I were to define a macrostate, where I said a macrostate, if I'm playing poker, the macrostate is that I could get a crummy hand, or I could get a spade royal flush, which would help me win. Those are my 2 possible macrostates. The macrostate of a crummy hand has more microstates associated with it because there could be other combinations of 5 cards that would be equally crummy. And so a macrostate that's defined as a crummy hand would have more microstates associated with it, and hence would be more probable, because each microstate is equally probable, than a macrostate that was a spade royal flush, because that only has, in this case, only 1 microstate associated. What do you think?
The one on the
That was
right,
a very good description.
the one on the right is the AM, is AM time in the casino, and the one on the left is when about midnight.
Why do you recognize the cards?
No, that's after you see the waitress a few times.
Oh, okay, I see.
Those free drinks, yeah.
Yeah, this is
To a casino or
from Vegas.
Yeah.
This is to study microstates and macrostates.
I think it's totally justifiable. We might be able to get government funding also.
Let's try another example. Suppose you have a bag with 50 red marbles and 50 green marbles. When you draw a marble, you reach into the bag, draw a marble, any marble, pull it out, record its color, return it to the bag, and then draw another. So you go into the bag, and first time you pull a red marble, right? And then you put that back in the bag, dip in again, pull out another marble, and now you pull out the green marble. All right? Put that back in the bag, and continue until you've chosen 4 marbles. So you choose another one, another red marble, and choose another one, and oops, red marble. Right? I got 3 red marbles and 1 green marble. What are the possible macrostates and what are their probabilities in choosing 4 marbles out of this bag, returning the marbles every time after you've chosen them, but you record what you chose? All right? Well, here's the results. If you chose 4 marbles and you ended up with 4 red marbles, the possibility of that happening in your 4 choices is one possible microstate. But as you're choosing, if you were to choose 3 red marbles and 1 green, you could choose the first 3 as red, and then your last one is green, or the first 2 is red and your third one is green, or each, substituting in for each choice one of the greens. There's possible 4 microstates associated with choosing 3 reds and 1 green. And if you were to choose 2 reds and 2 greens, there's a possibility of 6 microstates for that. Likewise, choosing 3 greens, 1 red, possible 4 microstates for that. Choosing all green, just 1 microstate. Total number of microstates is, 16. So your probability of choosing all red would be 1 in 16, which I guess would be the probability of 1 microstate. The probability of choosing 2 green and 2 red, which would be the most disordered state actually, would be 6 out of 16. The most ordered are the least likely. All red, all green are the least likely state that you could choose, whereas the more disordered state is the most likely in terms of probability. So here's a statement of entropy in the second law. Entropy, which we designate by S, is a measure of disorder and can go like this. The entropy of the universe increases in all real processes because as a process develops, more microstates are possible. There was an original idea of entropy, and it involves heat. And the statement of entropy before it was taken over by the statistical mechanics people was that entropy could be, it was a state variable, and it could be defined as the following. Let the amount of heat added to a system in a reversible process, the amount of energy transferred by heat when the system follows the reversible path. Then we define entropy, the infinitesimal change in entropy, ds, is defined as the infinitesimal change of heat added in a reversible process divided by the temperature of the system at that moment. Change in entropy only depends on the endpoints, not how you got there, not independent of the path. So it's not a transfer variable, it is a state variable. So how you started, how you ended, the change in that is what's important, but not how you got there. This infinitesimal change in heat along a reversible path may be used even if you followed a irreversible path, because again, the change is important on a state variable and not how you got there. So you can choose the reversible path that you wish. So the meaningful quantity is the change in entropy, not the entropy itself, and the change in entropy would be the same between 2 states. If you had a finite process and you were to add up all these infinitesimal changes in entropy over that interval, you would get the total change in entropy between 2 states, and that would be the integral of all this heat added through a reversible process over temperature. Bear with me, we're going representation for this unknown. Which this is not that bad.
Yeah.
We are free to choose any particular reversible path we wish, and the actual path doesn't matter as long as the initial and final states are the same, because we're changing between 2 points of a state variable. We're going to show some examples. Here's a change in entropy for a phase change. Say I'm going to go through a phase change, for instance, changing ice into liquid water. All happening at the same temperature. So it's all going to happen at 0 degrees Celsius. So any phase change can be isothermal, involves the heat of the phase change, either the latent heat of fusion or the latent heat of vaporization. And so we can set up our entropy change. That's integral from the initial to final of the change in heat through a reversible process or the temperature, but it's isothermal, so the temperature is constant. So I can take that out of the integral and just evaluate the change in heat, add it, and that would just be the heat added to the reversible process divided by the temperature. In this case, that is the heat of the phase change. If it were going from ice to liquid, then it would be the latent heat of fusion divided by the temperature. So the change in entropy for a phase change is just your latent heat divided by the temperature. Let's try this out. Here's problem number 19 on the handout, or the chapter 22 handout, which is not a handout that you already have in your notes, but it used to be a handout. 500 grams of ice melted at a temperature of 32 degrees Fahrenheit. What is the change in entropy in units of joules per Kelvin? 32 degrees Fahrenheit is 0 degrees centigrade, and that will be 273 degrees Kelvin. So you want to make that change to Kelvin right away. 500 grams of ice went through a phase change. Our change in entropy is the latent heat of fusion, the mass times latent heat of fusion, the heat associated with the fusion. So that's going to be 0.5 kilograms, that's 3.33 times 10 to the 5 joules per kilogram over 273 Kelvin. There's a 610 joules per Kelvin. This change in entropy is positive. What that means is that this is a likely thing to happen. If you get a positive value of entropy, that is an evaluation of whether that process would occur spontaneously or not. If you had a reversible cycle, the change in entropy is 0, because you can reverse easily between the state back to the same state. So the change in entropy should be 0 by definition. And we'll consider, for instance, the Carnot engine, which we've stated to be a reversible process. In a Carnot engine, if you're having you have an isothermal process at a hot temperature where you take in heat, and then you have an adiabatic process between two temperature zones, and then you have an isothermal process of compression at low temperature, with compression at low temperature. And so you exhale heat in that process, and then you have another adiabatic process between temperatures. So in the adiabatic processes, no heat is taken in, so we don't have to consider the entropy change of those. But we have the entropy change where we take in heat at the hot temperature, and entropy change where we give off heat at the cold temperature. One's going to be a positive value, one's going to be a negative value. But we also know for a Carnot cycle that the heat exchange to the cold reservoir over the heat exchange to the hot reservoir is equal to the same ratio of the temperature of the cold reservoir to the temperature of the hot reservoir. if I were to solve this for Q sub C, for instance, plug it into here, then I would get the same expression minus the same expression. Which means that for a Carnot cycle, there's a little bit of algebra, I would get the change in entropy is actually 0. Now, for this definition of entropy, where you change the amount of heat in a reversible process over the temperature, and you can say you can choose any reversible process since you're going between two definite states, then if we have one reversible process, which we prove that the change in entropy is 0, that means that the entropy change for any reversible process must also be 0. Because I could choose this reversible process to stand for any reversible process. And that's, so I can prove that any reversible process has an entropy change of 0. What is the entropy change for thermal conduction? We'll say a cold reservoir absorbs amount of heat Q and its entropy increases by that amount of heat that it absorbed from the cold reservoir over the temperature of that reservoir. At the same time, a hot reservoir loses that same amount of Q and its entropy will change by the amount of heat that was given away from that reservoir, negative Q, assuming Q is a positive quantity, over the temperature of that hot reservoir. So since the temperature of the hot reservoir is greater than the temperature of the cold reservoir, the increase in entropy in the cold reservoir is greater in magnitude than the decrease in entropy due to the hot reservoir. So for the system and the universe, the entropy would be, this would be greater in magnitude than this, so the entropy will be a positive one. Because you have positive entropy from absorbing heat into the cold reservoir and a negative entropy from losing heat from the hot reservoir. Net result, universe entropy goes up, and this is a likely possibility. Let's try this out with the problem. Which way does heat flow? Let's say we have a large cold object at 273 Kelvin and a large hot object at 373 Kelvin. Show that it is impossible for a small amount of heat, say 8 joules, to be transferred from the cold object to the hot object spontaneously without decreasing the entropy of the universe and hence violating the second law of thermodynamics. Well, what we're talking about is possible heat exchange spontaneously from cold to hot. If we were to calculate the entropy change, well, for the hot reservoir, since we're taking in this amount of energy, then that would be 8 joules over 373 degrees Kelvin. So that would give us an entropy change of 0.0214 joules per Kelvin. Anytime you're taking in heat, that's assumed to be a positive quantity. Since we're losing heat from the cold reservoir in the form of 8 joules, and that change in heat would be minus 8 joules over the temperature of the cold reservoir, 273. So we have minus 0.0293 joules per Kelvin. And as the universe is concerned, both these processes taking place for this extraction of heat, then the net entropy change for the universe would be a negative 0.0079 joules per Kelvin. Since that quantity for the universe is negative, we would say that this is an unlikely process. That you would actually take heat from a cold reservoir, have it spontaneously go to the hot reservoir. However, the reverse of this would be true. That if you were to reverse this, if you were to take heat from a hot reservoir and expel it to a cold reservoir, your value for entropy would just be the positive value of this. and hence that would be a likely occurrence. So it's by the second law of thermodynamics, it would govern, this idea of entropy would govern the idea that spontaneous heat exchange from a hot object to a cold object would occur, but not vice versa. Let's try this problem. A 70-kilogram log falls from a height of 25 meters into a lake. If the log, the lake, and the air are all at 300 K, find the change in entropy of the universe for this process. So we have a log. It's going to fall into water. I'll just put the spill there. We're going to assume that nothing's spilled, actually. And all this energy just goes in to lake. Like we did on the problems on the board earlier, all the energy we're considering here is just the potential energy of the log. We're going to say that all that goes into heat. So that's going to be mgh, in this case 70 kilograms, 9.8 per g, 25 meters per h, 1.72 times 10 to the 4 joules. All this is done isothermally at one constant temperature of 300 K. So the entropy of the universe will be that amount of heat over that temperature, entropy change, 1.72 times 10 to the 4 joules over 300 Kelvin, 57.2 joules per Kelvin would be our entropy change for the universe. So far, so good. The entropy change for an isothermal process. Consider isothermal process. Both the heat of a reversible process and the temperature depend only on the temperature, and that is a constant. So we have the change in entropy is the integral of the heat added in a reversible process over the temperature. But the heat added in a reversible process is a function of volume and the temperature, but the temperatures cancel out here. If we were to integrate this from initial volume to final volume, we would get NR, natural log of the final volume over the initial volume. This is slightly different from your notes because I just made a correction on it, but the answer is the same. So this is our entropy change for isothermal process. Is basically only dependent on the natural log of our volume change. And the entropy change for adiabatic free expansion. Consider adiabatic free expansion where you start with a gas and the gas is insulated from the outside, from the surroundings. But you take away a membrane and you allow that gas to expand into the open area so that it fills up a larger volume. We call that adiabatic free expansion. Q is equal to 0 because we have no exchange with the outside world from the system, but we can't use that because that would be for a irreversible process. So what we use is actually the isothermal process between the two states. Because since change in entropy or entropy itself is a state variable, all that matters is what happens between your initial state when you have the gas confined to a smaller volume to your final state. And so the entropy change will be the same. So we just figured this out for isothermal process. So for adiabatic free expansion is exactly the same change in entropy. Since the final volume is greater than the initial volume, this change in entropy will be positive. So it's likely to occur that you would have the gas expand into the greater volume, but not likely that the reverse would be true. If you had a gas with a certain volume, that all of a sudden it would find the microstate where it was confined in half the volume, and the rest of it were vacuum. not likely. Which is a good thing, right? We're breathing gas in this room, and all possible microstates are possible. It's very nice that the one microstate where the gas would separate to the sides of the room and would be in a vacuum and couldn't breathe. That's not likely to occur, right, according to entropy. Just to give you that thought, being a true physicist, right? This indicates that both the entropy and disorder of the gas increase as a result of the irreversible adiabatic expansion. A lot of stuff here, huh? Is there a change in temperature of a substance? The entropy change for that, we can calculate based on the change in heat added for a reversible process, mass times the specific heat, times the change in temperature. We integrate that over the temperature. We find it does depend on temperature, and integrate from initial to final. We get that the entropy change is the mass times the specific heat times the natural log of the final temperature over the initial temperature. The substance of the gas and the temperature variables are not given, then use the ideal gas law to find the ratio of the variables that are given. In other words, if it were a gas expanding at constant pressure, then you could use this ideal gas law and eliminate the pressure on both sides, get a ratio that would of volumes as they relate to a ratio of temperature, and just plug that in here, and then you could use the same formula. Make sense? So here we go. Here's a summary. This is probably what you would need on your formula card, I guess. For isothermal heating or adiabatic free expansion, the change in entropy is N, number of moles, times R 8.31, times natural log of the final volume or the initial volume. For conduction from a temperature reservoir at constant temperature, the change in entropy is the amount of heat involved in that conduction over the temperature of the reservoir. If it's going into the reservoir, that would be a positive entropy change. If it's going out of the reservoir, that would be a negative entropy change. In other words, heat going in would be a positive quantity, heat going out would be a negative quantity, just like it is in the first law of thermodynamics when we use that. Isothermal phase change, the amount of heat involved in the phase change over the temperature. Heating a substance with an associated change in temperature, that is the mass times the specific heat times natural log of the final temperature over the initial temperature. Heating a molar gas with associated change in temperature, where the molar heat, specific heat, is at constant volume is C sub V, or constant pressure C sub P. That would be derived using the same kind of formula as we just derived. That would be the number of moles times the molar specific heat times the natural log of the final temperature or the initial temperature. And for a reversible process, change in entropy is 0. So you just have to read the problem and know what situation you're looking at and use the associated formula for the change in entropy. Therein lies the problem. Right? Eventually, if things proceed as we go from one macrostate to the next macrostate, and we develop more possible microstates, especially with every kind of energy conversion, ultimately the entropy of the universe should reach a maximum value. Ultimately. At this value, the universe will be in a state of uniform temperature and density. All physical, chemical, and biological processes will cease because that was what involved entropy change. The state of perfect disorder would imply and no energy would be available for doing work, a state would be called the heat death of the universe. Or what I like to call the ultimate vacation. No energy to do work. Great. Just relax the whole time. On that good thought, let's conclude thermodynamics. Kind of looking forward to that heat death of the universe. I tell you, yesterday, I don't know what happens. Every once in a while, the circuit breaker goes out or something. The rooms get really hot up there. Yesterday, it was about 79 or so. No. Do you know? Oh, really?
I think so.
So you have to go in the president's office to flip the switch?
From what I've been told, I don't know how.
We can't hear the ocean in this room.
And
We'll put it
luckily,
upstairs.
this is the business executive, because this president is. To be in this building, because if we were down there with nursing days, then we wouldn't have it. Because it's not for me,
Zach had it that night.
really.
Let's try a couple of these problems from the end part of chapter 22. You can look at number 18 in chapter 22.
18.
18. So since latent heat of ice is 333 joules per gram, write that down. The change in entropy in calories per kilogram when 1 kilogram of ice melts is, well, this would be a phase change involved with this entropy change. So the change in entropy would equal the mass times latent heat of fusion for water over the temperature. And we were given the latent heat of ice, but we're told to calculate it in calories per Kelvin. So I'm going to use the value of the latent heat of fusion in terms of calories. So this would be, you're at 1 kilogram, and this would be 79.6 calories per Kelvin over the temperature of the system, 273 Kelvin. So if I were to calculate that, what would I get?
Wait, what number are we on?
Isn't that 18? In chapter 22?
This is
Yeah, I know, it just says.
Oh, it says, yeah, there's a typo on the top of the page that says chapter 19.
I just
Oh, okay, all right. I was getting confused there.
Yeah. There's a few typos in these notes in the column sets because this is the first version that's made it through the published. Yeah. Wait with you for that? Can someone figure it out for me? Yeah, entropy.
Well, that was why there's chaos on it.
291.58.
91.58 calories Kelvin. Yeah, the microstate associated with having a typo on this page was the one that came up for this macrostate. Right? Actually, it's a pretty good macrostate because most of the letters and numbers are in the right place. So you just have one or two that are out of place. Take a look at number 20 below that. It says determine the change in entropy in joules per Kelvin in 5 moles of an ideal gas at 0 degrees Celsius are compressed isothermally from initial volume of 100 cubic centimeters to the final volume of 20 cubic centimeters. Well, we derived this formula just a moment ago, and so we look at our trusty formula card. And for isothermal process, the change in entropy is the number of moles times R times the natural log of the final volume or the initial volume. In this case, we're going to compress it from an initial volume of 100 cubic centimeters to the final volume of 20 cubic centimeters. 5 moles, so it's 5 times 8.31, natural log, final volume of 20 cubic centimeters, initial volume of 100. I don't have to convert cubic centimeters because the units cancel out. So as long as it's a good ratio, I'm okay, as long as they're in the same units. So this would be 5 times 8.31 times natural log of 1/5. What does that give me?
Negative 66.9.
Negative 66.9 joules per Kelvin. Because we're taking energy from the universe to do this process itself would have a negative 66.9, but if you consider all the entropy change of the universe and surroundings, you would come up with again, a positive value entropy change for the universe. We're just looking at the entropy change for this particular gas. Take a look at number 22. Twenty-two. 10 kilograms of water at 0 degrees Celsius is mixed with 10 kilograms of water at 100 degrees Celsius. The change in entropy of the system is if we had water changing temperature, just any kind of quantity of water changing temperature, we would associate the change in entropy of that as the mass of the water times the specific heat of the water times the natural log of the final temperature over the initial temperature. That was one of those formulas we just derived as well, but in this case, we've got 2 reservoirs of water, two quantities of water. One that's going to go from 0 degrees to some final temperature, and the other quantity that's going to go from 100 degrees down to some final temperature. So we'd have to calculate the entropy change for both of those quantities of water. Is what we would have to do.
Can you send people to each other since the entropy of both systems will change equally?
Well, that's the whole thing about entropy, though, because this fraction of the final temperature and the initial temperature won't be the same. That's what will make this interesting. All right, first of all, we've got 10 kilograms of water at 0 degrees Celsius. So here's M1, 10 kilograms, 0 degrees Celsius, or 273 Kelvin, or temperature, called T1. And we have over here mass 2, also 10 kilograms. Temperature is equal to 100 degrees Celsius, or 373 Kelvin. Very close to boiling. We add a little bit more energy. And we're going to pour them together. Our final state will have 20 kilograms. What's our final temperature? How could I find the final temperature? Yes, exactly. The heat gain over here will be equal in magnitude to the heat loss over here. So we could say that M1, C1, delta T1, at least in magnitude, equals M2, C2, delta T2, at least in magnitude. But the two masses are the same in this case. They're both 10, so the masses cancel out. They're both comprised of water, so the specific heat is canceled out. And this magnitude of this temperature change 1 would be equal to our final temperature minus our T1. And the other temperature change will be our initial temperature minus T, our final temperature. Now let's put the numbers here. Final temperature minus 273, we go to 373 minus the final temperature. Add a T to both sides, bring this 273 over here. So I have 2T would equal 646, or T would equal 323, which kind of makes sense. If I have equal amounts of water, one at 0 degrees Celsius, the other one at 100 degrees Celsius, and I pour them together, the final temperature will be right in between at 50 degrees Celsius, 323 Kelvin. Okay. So that's going to be our T final for this entropy change. So if I say for the cold water, our change in entropy, called cold, will be equal to the mass of the water, 10 kilograms, times the specific heat of water, 1,186 joules per Kelvin. Joules per kilogram. Natural log. Final temperature would be 323. Initial temperature 273. What do I get for that?
About 7K.
7,000
Yeah.
exactly, or?
No, it's like 7.04 times 10 to the 3.
All right, let's do that. 7.04 times 10 to the 3 joules per Kelvin. If I did the hot water, entropy change for that, it's going to be 10 kilograms times 4,186 joules per the initial temperature, 373.
Negative 6.02.
Negative 6.02 times 10 to the 3 joules per Kelvin. So our total entropy change will be the sum of these two, of the cold and the hot. That's going to be 7.04 minus 6.02 times 10 to the 3, or about 1.02 times 10 to the 3 joules per Kelvin. Positive. So that's a likely occurrence. It's a process that would occur. Okay, we ended up with joules per Kelvin. They want it in units of calories per Kelvin. So I guess you'd have to divide that by 4.186. So entropy change is 1.02 times 10 to the 3 joules per Kelvin times 1 calorie of 4.186 joules. And if I divide 1,020 by 4.186, what do I get?
2.43 times 10 to the 2. 243.
43 calories per Kelvin. You're right. What do you think? Enough? All right, let's stop there. Test next Monday. There'll be a matching page